jurisdictions. And I think we can say confidently that in 2020 we are within reach of the promise of Source as a truly national platform, with the benefits of standardisation brings in terms of community practice and collective development and maintenance. Source as our national platform is assisting with our international relationships. In September, the Government of Australia, through our ambassador in Phnom Penh, offered access to eWater Source, supported by capacity building and river basin modelling, to the Government of Cambodia's Ministry of Water Resources and Meteorology. The offer was warmly received as part of Australia's ongoing commitment to support sustainable management of water resources in the Mekong. A few quick software metrics. Total Source users, about 6,412 to 4 significant digits in 100 countries. We have about 1,245 music users, which include 381 Music X users in 18 countries. In 2020, we added 81 new music users, 17 new full Source users, and over 1,000 new Source public users. The Source public version remains very important because it's been designed to fit with teaching programs. And at the moment, eWater tools are in active use for teaching and research in around 20 universities around Australia. So the Source public version performs a very important function as a teaching tool. And presently we have 856 support contracts under management. So support is continuing to be very strong, and with a strong release of updates and upgrades, we are committing to support our community. Training has been something of a revolution under COVID. We have provided 208 training seats since the 1st of July, which compares very well with the total of 278 in all of the financial year 1920. So we are not far off in 6 months what we did in 12 months last year, and 193 in 2019. So training is growing significantly. Training has been a huge success since we moved to 100% online. As we move forward, there'll always be a place for face-to-face and the personal guidance of trainers. But the online experience has been very positive, and we plan to expand the range of training options significantly in 2021. With the widespread adoption of Source for river and catchment analysis, and music already standard for water-sensitive urban design, the time has finally arrived to deliver the integration outcomes foreshadowed by the eWater CRC. Let me show you what that will look like. And so I'm going to share my screen, and I'm going to share that one. So if we look at a city within a river basin, so just some broad elements. We have a reservoir, we have a feedlot or some agricultural production, a groundwater fed crop. These are the rural side of things. We divert water from the river to the water treatment plant. We have urban and peri-urban residential, we have a commercial centre, some playing fields, stormwater pond, a sewage treatment plant, a wetland, and these make up the sort of broad elements that you would see in a city that's sitting within a river basin. Source is the model that supports the planning and operation of rivers and catchments through the entitlements and allocation system. We can accommodate and describe all of those sort of river-based elements at a fairly coarse scale. But what we can't do in Source is we can't describe the detail of the city demand or the urban demand. So the urban demand tends to be lumped as a time series or a function, and there's no feedback for changes in the allocation system and the demand. There are some demand curves, but it's not a dynamic feedback system. And likewise, the runoff from the city is just a lateral catchment inflow and doesn't address some of the detailed city elements. Urban Developer was a tool that was started in the CRC, but really has not been taken much further since the end of the CRC. But with the help of Melbourne Water, we have now built a plugin for Source around Urban Developer. Urban Developer allows us to detail the use and reuse of water in the urban landscape. Grey water tanks, rainwater tanks, recycled water from the treatment plant, rain gardens, etc. So Urban Developer allows us to accommodate integrated water cycle management aspects within the urban landscape and adjust the urban demand according to the effectiveness of those elements. So now the diversion from the river system includes demand management and recycling. So that comes with the Urban Developer plugin. Then we have music. Now, traditional music is a Fortran Delphi application, so not very well suited to integration, but Music X, we have converted music into the C# code base, and so it now can form a part of the broader Source. Music X is a standalone product. What I'm talking about here is the plugin. So when you have a Music X plugin to Source, that's when you can actually build them all together. And music, of course, contains all the water-sensitive urban design elements: sedimentation basins, runoff, gross pollutant traps, bioretention, wetlands, swales, etc. So now the urban runoff into the Source model includes the urban water quality and quantity management. We bring those all together now, and we can actually design, using industry standard tools that we have through the eWater suite, integrate these elements together and design and manage a integrated urban system. The beauty of it being in the same base is that we can now make those cross connections. And these will come through custom functions or other plugins and elements which connect them together. So we can take the grey water tank through a bioretention and put it into the wetland. We can take the rainwater tank, run it through swales and also back into the wetland. We can then supply treated water through the wetland back into the demand system for outdoor use. The possibilities are endless, and the opportunities to represent the fully integrated urban cycle within the river basin is now there. Now the plugin for music plugin is yet to be released. It's coming soon, but it will have capabilities within the Source suite far more than music itself, as you can see here. I want to put a quick plug in for Jeff Davis's session later today on our new scenario management analysis tools. This is very exciting work of model provenance and how to manage scenarios running in the cloud and all sorts of exciting elements. I'm not going to steal Jeff's thunder, so just to put a plug in for that one. All right, so thank you so much. Have a great conference, and back to you, Trudy.
Thank you, Robert. You have to click so many times sometimes to make this stuff work. Okay, well, it is my pleasure now to introduce our first speaker, Katherine Szabo from HARC, Hydrology and Risk Consulting. Katherine has the illustrious title of having built the largest Source model, and she's going to show us.
Sorry, just lost me there for a second. All right, let me just share my.
All right, and I will disappear.
Sorry, it just seems to be on the wrong screen. Here we go. Alrighty, can everyone see your screen? Great, feel free to minimize my face and maximize the presentation. Completely fine with that. We've got a bit of detail in this presentation. My name is Katherine Szabo, and I am presenting on big models. So using Source to model 5,000 farm dams. Sounds like a big feat, but it was a really challenging and interesting project. I'd like to acknowledge Goulburn Broken Catchment Management Authority and DELP for us being able to do this project. And also big thanks to our project team. So we worked with Dr. Keir Fowler from the University of Melbourne, and Dr. Philip Jordan and Ella Guthrie from HARC also were big contributors to this project. Another thanks to Jeff Davis from eWater. So he was able to help out a lot and break through the upper limit of nodes in source so that I could build a ridiculously big model. So I got to the top limit and sadly couldn't go any further. So he was able to help that out. Oh, just gonna let me go next. Come on, okay. So our farm dam model was used for water resources modelling, climate change modelling, and environmental flow compliance. However, this presentation will primarily focus on just the modelling components and how I was able to use source to achieve project objectives rather than the results themselves. So I'll be taking you through a little bit of a background of farm dam modelling and our case study catchment, a little bit on model development, including some of the challenges we faced and some tips and tricks, as well as model verification and scenario modelling. So farm dam modelling is really crucial for understanding the extent of farm dam interception on surface water runoff and its impact on low flows in our stressed waterways. Previously, people might be familiar with using programs such as STEADY or CHEAT to model farm dam impact. Whilst you can model a network of farm dams, they're primarily lumped into a subcatchment, and it assumes an equal spatial distribution of runoff across the catchment. So you can't target dams in high yielding catchments compared to lower yielding catchments. Something really great that we still use with STEADY is the back calculation algorithm to calculate the farm dam impact on partial natural flows. So this will produce farm dam unimpacted flows, and I'll talk about how we use that in the next few slides. So the difference between using STEADY or CHEAT and source, so these are some of the really great benefits of using source, is that we're able to individually represent each farm dam with spatial distribution, including farm dams that are in high yielding catchments and low yielding catchments. By having these farm dams individually represented, we can target them with management strategies, as well as model the chainage of farm dams more accurately than a lump model. So what I mean about that is, say if you've got a farm dam in the most upstream part of your catchment, if you decommission that, there might be a farm dam downstream of that, and that water will just be intercepted by that farm dam. So with source, we can model that chainage and be able to work management strategies based on the chainage of farm dams. Something else that's really great is that we can integrate catchment and river systems modelling, and I'll show how we did that a little bit later on. As well, environmental flow compliance analysis can be done in different locations along the farm dam impacted watercourse, as well as climate change modelling. So this way you can really pinpoint improvements for different parts of the reach based on due to farm dam management strategies. As well, I'll talk about a few of the tools that are available to increase modelling efficiency. So our project was in the Seven Creeks catchment in northeast, so this little yellow square here, in northeast Victoria. The Seven Creeks catchment is part of the Murray-Darling Basin, and it flows into the Goulburn River. The catchment has been identified as a priority flow-stressed, unregulated waterway in the Victorian Policy White Paper, Our Water, Our Future, in 2004. At the start of the project, there was a need to better understand the impact of streamflow interception by dams on the Seven Creeks and how it can be improved by catchment management. So there's quite a bit of farm dam interception. As you can see, there's about 5,000 farm dams in the Seven Creek catchment. So the question that we're trying to answer is, what is the most effective management strategy to maximise autumn and summer low flows by reducing the impact of farm dams? And I'll talk about how we use source to answer this question. I'll take you through a little bit on the model development. There was a number of pre-processing, derivations and analysis required before we could get to this final point of a really nice farm dam model in eWater source. So each subcatchment required farm dam unimpacted inflows as runoff inputs upstream of each farm dam that could then be impacted by the individual farm dams. These natural flows in each subcatchment are split into the individual farm dams by the proportion of their intermediate catchment area. So first step was that we did derive partial natural flows by utilising the available stream flow gauges. We used rainfall runoff modelling and reach balances. Note that for the reach balances, we're able to derive in-stream losses and travel time, which could also be included in the source model. As I mentioned before, STEDI does have a back calculation algorithm, and we're able to use this to determine the farm dam impact based on the distribution of farm dams and derive natural flows that then went into our farm dam model. By natural flows, what I mean by that is that they're not impacted by farm dams. As well, we had to derive climate and demand time series for each farm dam as well, but I won't touch on that too much. The bigger process that we had to work through was trying to get all the farm dams physically into the farm dam model. So I'll talk you through what we did there. We picked up the DELC farm dam distribution layer, reviewed it and used it as the spatial distribution of farm dams in the catchment, and then a 10-metre digital elevation model. There's a tower dam process freely available online, and it stands for terrain analysis using digital elevation models. If you'd like more information, just Google tower dam and it's all online. So what that is a collection of tools that's able to extract and analyse hydrologic information from topography represented in the DEM. So we're able to calculate flow paths, slopes, and contributing areas for each farm dam using this process. This was then able to give us a farm dam layer and a DEM that was suitable to be put into the eWater source farm dam plugin. And what this is able to do is churn spatial layer and then pop it into a source model for you. As you can imagine, 5,000 farm dams is a lot. So I couldn't get enough computer processing power, so we had to cut these farm dams up into smaller chunks. And then I'll talk about what I did with that so that we could adapt to the computing processing power. So after all this, what we're able to produce is this. Looks a bit scary. It's very, very big. So this has got 5,000 farm dams in it, these little green triangles. And when you load this in from the farm dam plugin, it does clump it in a bit. So there is a bit of manual processing so you can get this nice sort of streamline here of the 7 creeks. As I spoke about earlier, we've got some in-stream losses modelled in there and travel time in the ARCs as well. What was really important that I mentioned before is we're able to integrate catchment modelling and river system modelling. So what we can do here is model the main urban demand centre of Euroa in our farm dam catchment model. So this gives us a bit more realistic results where there's urban demand water being extracted from the river, as well as farm dam impacts included, which we found really important for our modelling. A couple of challenges that we had while building this big model. Spatial analysis is quite difficult with just the sheer number of farm dams. Again, computer processing power was a bit of an issue there. So we had to write some batch files to separate the process up to chunks of about 1,000 farm dams so that we could run the spatial analysis without the computer crashing. As I mentioned before, I had some issues with the processing time and power required for the farm dam plugin. Similarly, I was splitting that up into separate little chunks, and I'll talk later about how I was able to combine them back up again. The runtime for 5,000 farm dams is about 1.5 hours. We didn't do anything on the cloud, but some people might find that as a better option. However, the bulk of my scenario modelling was only dealing with the upper catchments of 7 creeks. So I was able to do modelling with only about 1,000 farm dams and churn through it in about 20 minutes. As well, sometimes when you run your spatial layer through the farm dam plugin, it may not link up all the farm dams and just pop them in random spots. So I did find an easy trick so that you don't have to trawl through and find if there's any farm dams that aren't connected. So I'll talk about that in the next slide. So this is a great one that Jeff told me was the copy and paste function in source. So I had all these separate chunks of farm dams in different source models. So you could just drag and copy the entire lot, paste it into the source model that I was working in, and then that brought over all the functions, all the data sources, and then I could just link it up with what I was working with. So that was really, really handy. That gave me a model of the entire 5,000 farm dam 7 creek catchment. But what I also did is I separated it up into smaller subcatchments and connected them up via a linked analysis. So this allowed me to just do some modelling in the upstream catchments and then run a linked analysis so that impact went downstream to the downstream catchments. Another really great thing was the export summary to check linkages. So what you can do there is you just export a summary of the entire model and then just do a lookup with the farm dam list that you think is in the model and then a farm dam list of the linkages in the model, and that way you can find where's the missing link and do some manual checks. And this was a more efficient way of finding farm dams without connections. Something else that's really great is using scenario input sets for climate change modelling. We found this very efficient and easy. As you can see here, I can just click down and click on any of the scenario models that I'd like. So setting that up in Source is really great. And if you use this in combination with the hydroclimatic transformation tool that David from DELP will be presenting on this afternoon, that tool is able to load the climate change inputs straight into Source, and the scenario input sets can be used to group them up, and it's ready for modelling. Finally, probably one of my favourite things in Source is feature tables. You can imagine 5,000 farm dams is a lot to work with. So these feature tables allows us to export a feature table. We can do manual edits and quick lookups in Excel and load it back into Source so that we could decommission or make adjustments to the farm dams within seconds. So I'm sure you're wondering how well a model with 5,000 farm dams is able to match gauge flow. We had lots of verification points through the model. However, I'm just about to show you a verification at the very bottom of the Seven Creeks catchment. So this is a flow duration curve verification at the most downstream gauge. I nearly fell off my chair with relief when I saw this, so I was very, very pleased with the results. As you can see up here, there is a slight overestimation of high flows. However, when farm dam modelling, this is less concerning as farm dam interception won't have as much impact when the dams are full and spilling during wet periods. What we were really concerned about was the low flow fit. So this was a very good fit, and it verified that we can use this model to look at the impact of farm dams on low flows, particularly in the summer and the autumn. Our next step was to try and answer the question of which farm dams we can target and what management strategies we can use to increase low flows. So a couple of options we had was to decommission a farm dam or to put in a low flow bypass. So you're wondering, what is the best way to target individual farm dams? So we sort of split these up by looking at the top 5% based on total upstream catchment area. So the farm dams that intercept the most area, top 5% by farm dam volume. So this is important that they are able to capture the highest amount of low flow. And then also top 5% by location. So that's a little bit more of an optimized scenario. So what I mean by top 5% by location, this is just a map of how we were able to pick out different farm dams to decommission or bypass for scenario modelling. As I mentioned earlier, say if you were decommissioning this farm dam up here, sort of at the top of the streamline, if you don't decommission the next one down in the chain, then all the water will just get captured down by there, and then you don't get the improvement from your model. So that was what I mean by looking at location. So we're able to really target individual farm dams. A few things, I won't go through the results of the scenario modelling, but a few things we're able to do is look at unimpacted flow scenarios to show the impact of farm dams in the catchment, the impact of farm dams on cease to flow events, which is very important for environmental hydrology, environmental flow compliance assessment, and the impact of climate change on farm dam impacts. Just to give you a bit of an idea of what that would look like. So we've got the orange line is our base case, and then we're able to improve on low flow compliance during the drought years. As you can see, there's quite a bit of improvement on some of the other scenarios to show that there is quite a big impact of farm dams in this catchment. So there's a few different ways we're able to present the model, the results, but using Source really helped us output these models efficiently. So in summary, we're able to use Source to individually model 5,000 farm dams. This is a really neat way of integrating both catchment and river system modelling. And we're able to efficiently undertake scenario modelling to determine effective management strategies, particularly with the use of feature tables. As well, we could utilise the model and scenario input sets to undertake substantial climate change modelling. Now, unfortunately, I can't hand out any business cards for this conference, but if anyone would like to contact me with any further questions, that's my details there. And that's it. I'm happy to take any questions now.
Thank you. So at the moment, everyone's being a little bit shy and
Oh, that's right.
haven't sent in any questions.
They're welcome to contact me afterwards as well.
If someone does, then you've got 30 seconds. Otherwise, I thought it was really exciting to see how you'd used some of those input sets. I gather they might be a bit of an underutilised option.
Yeah, I can't recommend input sets and feature tables enough. The amount of time we spend on pre-processing and post-processing when you've got a tool like that there just really makes things easier.
Excellent. Oh, well, there's been a great presentation. Thanks. So well done. Here we go. Katherine, can you give us an example of a decision made using this tool?
Unfortunately, at the moment, this was all just a case study, more of in a business case stage. But sort of an example of what they could use it for is if, as part of the negotiation with farmers to decommission farm dams, you don't want to take that until you know what the impact of their farm dam is. So this way, you can individually target different farms where you can decommission or bypass those farm dams, and then really make an educated decision on whether it's worthwhile for the catchment. Otherwise, it's probably not worth having such a difficult conversation with farmers. But this is still just in the preliminary stage and hasn't been rolled out.
Cool. All right. And I'll do one last question from Lydia. Second, how far do you think you could push source for the number of nodes? I'd say the sky's the limit.
Or Jeff was just in 10 seconds able to give me more nodes. So I'd say in this one with the farm dams and the linkages and things like that, it'll end up being about 7,000. And yeah, I'm not sure about the back end of source, but you're trading off the increase in nodes, you're going to be trading off processing time and things like that.
Sure, excellent. So, well, Jeff looks like he wants to say something.
Yeah, he can comment more.
Quite a few extra questions came in. I would encourage you to send Katherine a message or jump on her table and ask her those questions in one of the breaks. There's some pretty good ones there. So thank you very much, Katherine. I'll let Jeff can say what he's going to say, and I will invite our next speaker up on the stage.
Sure. It was the node limit was put in there historically when we used a different algorithm to calculate network run order, but we've moved on from then. So the limit, we actually just removed it. So there's no actual limit now on nodes, but it will be limited by the runtime and your computer.